If you want to get your head around it, it certainly helps to get started. Even if you're interested in doing mostly something like high-level synthesis, it really helps to sit down and do some of the hardware description coding.
The thing to get your head around, as my guest for this episode, Michael McLeod, has just mentioned, is called the Field Programmable Gate Array, or FPGA for short. And in the next few minutes, we're going to explore what they are, what they're used for, and how you work with a computer like that. Earlier this season, I talked about analog computers with my guests Bernd Ullmann and Daniel Turk. And if you listen to this episode, you'll know that analog computers work quite differently compared with the kind of machines we're used to, like your laptop or mobile devices. Well, FPGAs, Field Programmable Gate Arrays, are another class of computers that break the mold of your standard computer design and architecture. But compared with analog electronic computers, FPGAs are relatively recent. They became available in the 1980s, with the first commercial FPGA produced by the company Xilinx in 1985. Xilinx became part of AMD, who still continue producing high-end FPGAs. As the name suggests, the main principle of FPGAs is that the logic and circuitry inside is programmable, which makes them very adaptable and therefore interesting for a wide range of applications. But, like analog computers, they require a very different way of working with them. And to talk about all of that, I met with Michael McLeod, Senior Research Software Engineer at the University College London and a former colleague of mine at UCL. Michael has been working with FPGAs for a while in some of the projects at UCL, as you can hear now from my conversation with him. Hi, Michael.
Hello.
We're talking about FPGAs, so
Yes.
Let's start with what they actually are.
So FPGA stands for Field Programmable Gate Array, which on its face probably won't mean anything to you.
No.
The basic idea is that what you have is almost like a blank slate of a circuit. So you have lots of small pieces of logic, like lookup tables, which you can think of as logic gates.
Yeah.
Replicated many, many, many times across this like large, essentially a grid.
Okay.
And you can conceptually think of it like as though these are all linked by little switches. So when you are programming the circuit, when you are designing it, what will happen is essentially you can think of it as closing certain switches to link up the circuit in a specific way to connect certain bits of logic and not others. So it's essentially a totally customizable circuit that you can load a hardware design onto.
Okay, so the sense of the difference to ordinary computers where you basically have the circuit already given, the many different things, you can program it or you can change it.
I mean, a typical computer, has a fixed circuitry and it has a very specific way of operating. So the idea of being programmable is very different in the case of a typical CPU running software.
Yeah.
So that idea, just for like a brief overview of von Neumann architecture, you have a program in a special area of memory. And what the CPU does is at each step, it will read the instruction from the program and perform one of a set of operations that it can do. It will load something from memory, or it will perform a multiplication, or it will put something into memory, and so on and so forth. And in that sense, it is programmable because you are loading different programs into memory, so it will follow the different set of instructions. But what the hardware is actually doing is the same every time, in that it's always doing this read and then operate and then read and then operate continuous loop. The way that the circuit itself is like working is kind of always the same.
Okay, and in FPGA, it's obviously different because the circuit is not the same.
Yeah, so in FPGA, you're not loading a program into memory. You are modifying the circuit itself, and the circuit itself will be designed to do one task. I mean, in principle, because it is such a blank slate, you can actually use an FPGA to build a CPU. You can make a von Neumann machine on an FPGA if you really wanted to. There is a whole field of doing emulation on FPGAs of old machines. Like it's a way of doing hardware preservation. So
Right.
you can actually run old programs on an FPGA if you can recreate the architecture. But generally speaking, for an FPGA, you're creating a specialized circuit that does one thing. And then to solve another task, an FPGA can be kind of reset and then all the wiring reprogrammed to do another task. So that's what sets it apart from an ASIC, a specialized chip.
Okay, so programming an FPGA is then very different to, say, programming for a ordinary computer with a CPU, with a central processing unit, where you write the program up front in, say, Python or C++ or Fortran or whatever. But what do you use in order to program FPGAs? You're not actually going in there with wires and resistors and sort of...
No, you're not going in there with your soldering iron. With an FPGA, there are two main approaches. The main approach, the traditional approach, the most effective approach, is the same as it would be if you were designing a custom chip, if you were designing an ASIC in industry, and that is to use what's called a hardware description language. So hardware description languages, the most popular being VHDL and Verilog, are languages which allow you to define how logic circuits work. So you can define components, and then you can define how those components connect together. And you're very much explicitly dealing with signals, digital signals that are coming in and flowing out of your circuit. And in this sense, it's very different conceptually to the way that you think about programming software. You're not thinking about it in terms of a sequence of instructions so much, but you're thinking of it as a circuit. So you've got data flowing through logic gates, and everything that's happening in a circuit is kind of happening at the same time. You're not thinking in that sequential way necessarily that you do if you're writing like a C program or something like that. So on the one hand, it's a very different way of thinking, and it's a different kind of language, but it allows you to specify exactly how many bits you want to be dealing with and how much parallelism you want, and all of these like really very highly configurable things. You're not restricted to what that language, your programming language and your CPU offers you. If you're working on a CPU, you're always working from this kind of limited set of data types and instructions that it's built to already handle. The second approach, if you haven't done any like hardware design stuff, is to try what's called high-level synthesis. And high-level synthesis is an approach that attempts to take a program written in a language like C or C++, which has been decorated with usually some special extra statements to try to give the compiler some hints about kind of how much parallelism you want or how you want it to handle things. And it will try to convert that into a circuit design. So it will essentially try to translate that into a hardware design as opposed to running on software. And this is obviously a very tricky problem to solve, so it doesn't always work that well. And you run into some issues because, in my experience at least, it can be difficult to express exactly what you want because languages like, say, C are very tied to the idea of the von Neumann architecture. Yes. It is a sequence of instructions that are intended to be kind of read and executed in this way. And it doesn't have any like notion of this kind of parallelism or any way to really properly express when you want specific ideas in the circuitry. And so it can be very difficult to get what you want. It can be very trial and error. So it's a possibility, and it's something that people are experimenting with and looking into, but it has like serious limitations at this stage.
You mentioned parallelism quite a few times now. Is that the use case for FPGAs then?
It's a big part of why it's useful, although the parallelism in an FPGA often is a little bit different to the kind that you might meet on, say, a GPU, or what you would normally be doing if you were programming for clusters or something like that. The idea that you're usually striving for in an FPGA context is a pipelining kind of parallelism.
Right.
So if we compare to something like a GPU you will typically load on a lot of data,
an array.
and then you will process that data on lots and lots of parallel threads in lockstep. So they're all the data is experiencing the same changes at the same time. You just have like lots of pieces of data. So it's called batching, this approach to parallelism. You load up a big batch and then you process it. With an FPGA, because we don't necessarily have to process in lockstep, we can think of it more in terms of the way that data flows through a circuit. So let's say I have a sequence of operations that I want to perform. Then I can take my first pieces of data and they go into, say, a multiplier. Let's say that once that multiplication is done, that data moves into an adder, let's say. And the next piece of data that's flowing in from my data input can go into the multiplier while my first piece of data is in that adder. So, so they're all kind of moving along a pipeline. So there's lots of operations going on in parallel, but not necessarily the same operations happening to all the data. It's different pieces of data are at different stages of the pipeline at the same time. And the goal for this is generally to try to take up the data and into the pipeline at the same rate that it's coming in. And then after whatever latency of your circuit to output the data at that same rate as well, which makes FPGAs extremely popular for real-time applications. So real-time data processing, things like digital signal processing, video processing, sensors, that kind of thing.
All right, that's what I want to come to next, actually, the application of it, because I think you worked on them for a while. I remember that while we were together at UCL, that you had a project with FPGA. You were experimenting with it.
Yes,
but maybe you can explain a bit more what that was or is.
We were experimenting a bit with Markov chain Monte Carlo methods, which it's a statistical method for inferring parameters. I don't know if we want to go into too much detail about it, but it's an area in statistics that is useful in science for inferring, say, the parameters of a model that you're investigating based on the data, real world data that you have.
So, for instance, in physics, you might think of that like mapping a path of a particle through a detector, for instance?
Well, it's anything that you might want to kind of work backwards from your data to. So an example from my own personal experience in astrophysics is, let's say you want to understand some of the fundamental constituents of the universe. So you'll say how much of the universe is dark matter, how much of it is regular matter, how much of it is dark energy, like what's the Hubble constant, all of these, there's all these different components that go into our model of how the universe works. But in the physical mathematical models that, these are all linked by equations, but they could have different values. So how do you find out what values these actually take? What are the actual ratios of these components and so on and so forth? Well, we can look at, say, data from galaxy surveys or the CMB or something like that. And what we can do is essentially we take a sampling approach, which means we try out lots of different combinations of values and we calculate what we expect the galaxy distributions and the CMB to look like under those circumstances. And we essentially are exploring this space of possible values until we kind of hone in on what the most likely ones are, the ones that best fit our data.
And that's the kind of example of a Markov Monte Carlo simulation.
Yeah, I mean, so generally a sampling problem, and Markov chain Monte Carlo is one approach to sampling.
Okay, and that's where FPGAs come in then.
Yeah, so we were taking a look at implementing a particular MCMC method on an FPGA to see if we could accelerate it a bit. And we were specifically looking at what could be done using the high-level synthesis tools rather than the hardware description languages, because we wanted to try to look at like the accessibility of this problem, like FPGAs to more general scientists who usually won't have any hardware background. So that's why I know about the limitations of this kind of approach, because we felt them quite deeply when we were trying to do this. Another issue that we kind of ran into is, you need quite a lot of parallelism sometimes to make up for the fact that the clock speeds are slower on an FPGA. So you're not generally doing operations quite as quickly. And it tends to be better suited to, and this is a bit technical, but it tends to be better suited to fixed point operations rather than floating point arithmetic, which means that a lot of scientific programs need to change their thinking a little bit. You need to understand your domain well enough to know what kind of dynamic range of numbers you need.
Yeah.
Because the more bits that you can chop off, the smaller you can make your data, the faster it will be to run and the less energy you'll use and the more parallelism you can fit. So those kind of considerations are not usually major considerations if you're writing for a CPU, because you've got your doubles and your floats and your half floats, but that's most people aren't doing it. But this could be like, oh, I want this to be 7 bits wide, or I want this to be 13 bits wide. Like you really have a lot more control, and therefore you have a lot more to think about.
So where do you actually get the FPGA boards from?
It kind of really depends on your budget and what you want to do. Yeah, absolutely. There are very high-end ones being made by manufacturers like Xilinx and Intel. Realistically, like they're going to be purchased probably by an institution. They're very expensive. You can get hobbyist ones as well. I have a hobbyist one at home that is useful for learning on and trying things out. And they won't have very much space on like the circuit itself. They won't have as many resources. So you won't be able to build bigger, complex things, but you can certainly get to grips with the hardware design elements using something like that. And those might cost like 100 quid or something, maybe less even for some of the small ones. So there is actually a range out there. It just, for a lot of the practical applications, it will get quite expensive.
How hard was it actually to get your head around it? Because it's, as you said at the beginning, it's quite a different way and a different approach to programming, to the classical von Neumann computer. So how long did it take you to get your head around it and get into it?
That's a good question. I'm not sure that, I've even got my head around everything anyway. It's a big field, but I think if you want to get your head around it, it certainly helps to get started. Even if you're interested in doing mostly something like high-level synthesis, it really helps to sit down and do some of the hardware description coding, because it will help you to understand the fundamentals of how it operates and the difference between the way that you think about things like combinatorial logic, where things aren't happening in sequence because it's just a connected circuit, it's all happening at once, and you kind of have to get your head around that. I don't think it necessarily takes too long to do that if you're just willing to throw yourself into it for a little while. I think you can get to grips with it fairly quickly. I think the easiest way to do that is to just not try to think about it in relation to your imperative programming experience at all, and just kind of like leave that behind for a little while. I think especially if you've had some experience with functional programming, it will be a little bit more familiar, because functional programming is a more descriptive approach. It's not really about giving a list of instructions that get executed exactly like that on the machine. It's a little bit more abstract, and you're more likely to be thinking about the way that data flows through functions, and that can be conceptually a bit closer to like what you would be doing on an FPGA. So if you have some of that background as well, it might make it a little bit easier. But ultimately, I think if you spend a few weeks learning and trying things out and doing things in the hardware language and testing it on your little FPGA board, you'll pretty quickly get your head around the major conceptual difference. And then it's really about learning the vast expanse of things that you can do, which is with any field, like with regular programming, like with mathematics, like that's just it's almost infinite, right? Then I guess you just direct yourself to like what you're interested in and keep trying things.
If people are interested, this board that you bought for 100 quid yourself, where can they get that?
It's called the Go board, and it's produced by Nandland, which is a well-known FPGA/hardware design. Was a blog, and then they published a book. It's a good little starter board. It has like some buttons on it. It has a little segmented display, so you can play around with things like inputs and outputs and check that things are happening on it the way you expect. And that, I think, is less than £100. It's probably like 70 or something like that, I think. So that's a very like inexpensive way to get started. And then the software that you need to download to program the FPGA, because it needs some software to take your hardware design and actually put it onto the FPGA and figure out how to allocate the resources, because you don't do this resource allocation manually. Like it has to take your hardware design and check that it will fit onto the FPGA that you have. But that software it's free for personal and educational stuff. So so again, like no, you don't need to, there's no expense there. So it's a fairly straightforward way to sort of get started without investing in big fancy Xilinx FPGAs.
And we nearly forgot, Michael, the scientific applications of FPGA. You already mentioned something in astrophysics. Are there any other? Well, probably there are, but what are they?
As I mentioned before, a lot of the interest in FPGAs is in real-time data processing. In things like a physics context, that's often coming into the idea of sensors and detectors and that kind of thing for experiments. That's a really big potential area. The thing that's really good about an FPGA is it's not too expensive compared to producing an ASIC. It costs a huge amount of money to start producing because they're so specialized. Unless you're creating them at volume, it's really expensive. And also, if there's any bugs on it, you are ruined. You have to do it again.
You're doomed.
So an FPGA is very appealing, especially in science where you do not have that kind of budget and you're not producing satellites at scale, right? And crucially, you can fix problems on the go. Potentially like a lot of application in remote experiments, so things like satellites, or if you've got a neutrino detector in Antarctica or something. These are good areas like where you do not want to have someone go in and replace a chip because it's doing something wrong. You can reprogram it. As long as it's sufficiently shielded from the elements, it's quite good there. And likewise, any experiments where you're running kind of custom sensors that you want to be taking in information and processing it in real time. And that's like very broadly applicable across, a lot of sciences, that any remote experiments. I've seen quite a bit of interest in processing data for machine learning as well. Again, because they want to be processing lots of data in real time. Another advantage of the FPGAs is that they tend to have quite a low power usage. Unlike with, say, a more general architecture, you're not sort of powering these extra processes like reading instructions and doing things, and you're not powering anything you're not using. You're just focusing on the circuitry that you actually need, and that can be really effective. So again, a big plus if you've got something that is in space or somewhere awkward where the power supply, you want to make the most use out of that. Or even if you just have a data center and you're worried about your power usage. Another area that they seem to be popping up in is this Internet of Things. So the Internet of Things is this idea that's been around for a while, and that is about having lots and lots of connected components, like small devices doing different things all over the place that are connected to the internet in some way or can communicate in some way. When you're talking about like lots of small devices, again, like the low power usage, you don't want a general purpose machine for that, it has a specific job to do. In that case, you can potentially get really efficient, both like time efficient and power efficient solutions with an FPGA. An FPGA is a fairly cost-effective way to do that. So that's another area where they're sort of, people are interested in them and they're popping up.
That also means they come in different sizes.
The FPGA actual component itself can be very small. So if you were to, buy like a hobbyist board, the FPGA is only like a tiny part of that, and there's other bits with like connectors and everything that takes up a lot more space. I mean, you mentioned kind of like the hobbyist stuff and the really like high-end stuff that you might use for HPC, but there's everything kind of in between as well. So if you had an idea for a product that you wanted to make and you were going to be like, we're going to do a smallish run of them, like 1,000 or something, it's not worth it to try to invest in a custom chip, but it still needs to be an affordable-ish thing for people to buy. You can get a more affordable, less powerful FPGA if it will do the job for you. So they do come across like quite a wide range depending on what you wanted to apply them to. So there are different solutions available.
Okay, so there's actually quite a lot of action happening in this area then. It's what we're saying, not only in science, but also in commerce.
Oh yeah, there's a lot of industry interest in FPGAs. That's kind of where actually most of the FPGA stuff happens, because a lot of it is geared towards products, especially if you are doing smaller runs of a project or an initial prototype of a project, and you want to make sure that you can, so maybe you produce an initial run and you can fix any problems with it if there are problems with it. And then if it's popular and it's working, you might invest in a chip, a proper ASIC later. If you're producing at scale, it's much cheaper. ASICs are really cheap to produce once you get over the initial hump. So FPGAs, they're great for prototyping and for producing smaller scale commercial products. Academia is kind of starting to pay attention to this, but I think in academia, in addition to the sensors and experiment side of it, there's this big interest from the HPC side of it, of can we use these to accelerate high performance computing applications, so running on compute clusters, and can they rival GPUs for some of these applications? They tend to be looking often at fairly high end ones, because their whole point is that they want lots of parallelism out of it, which isn't always what you need from an FPGA. It's not necessarily always being used as this big accelerator. It's often being used just to be an efficient way to stream data through to do whatever kind of real-time application you want to be doing.
Analog computing, and there are certain parallels. I mean, first of all, FPGAs aren't analog computers. They are digital computers.
Yes. So we're dealing with digital signals generally with FPGAs, and we're dealing with digital circuits and that kind of Boolean logic gates. But there are, I think, significant similarities with the way that you're thinking in terms of constructing a circuit for an FPGA or doing analog computing.
So what are the parallels then? Let's talk about that.
If you're doing analog computing, the idea is that you're going to find some setup of a physical system, maybe circuitry or hydraulics or something like that, which is measurable and which obeys essentially the equations or the behavior that you're trying to investigate, that you're trying to compute. This is ultimately very frequently accomplished with a circuit where the signals will be analog signals. You're not measuring a 1 or a 0, but you're measuring along a continuum. But they're still circuits that obey the same behaviors that you're trying to investigate. If I want to, say, simulate a physical system that obeys this differential equation, we can build a circuit that also obeys this differential equation and look at what it does. Obviously, with an FPGA, as we've discussed, the idea is to build a circuit that also solves one specific problem or one specific family of problems. And you're often also dealing with the same idea of a continuous input and a continuous output. The main difference is one of them is essentially dealing with, say, a continual voltage signal or something like that. And the other one is dealing with this sort of stream of digital information. So with an FPGA, we're using a cutoff, and we're saying if it's above this, it's 1. If it's below this, it's 0. Because there's always some noise in the circuit anyway. They're still both just circuits built for a specific purpose. And as such, a lot of the reasoning can be quite similar. So if you think that you're building an analog circuit, you're not thinking in this sequential way that you would if you were programming a CPU. You're thinking about the circuit in this holistic way, all of the parts of the circuit are responding at the same time, at least up to how quickly signals can flow through a circuit based on physical limitations. But essentially, it's all feeding into each other at the same time, and all of that logic is happening at the same time. And that's the same thing that you get with an FPGA when you're doing combinational logic. So I think a lot of the actual thinking behind it is often very similar. And you're in some ways achieving similar aims, but you're working with different kinds of, you're just interested in different kinds of data, different kinds of signals. But the process of solving the problem, I think, has a lot of similarities.
Certainly in the sense that you try to model the hardware architecture, if I may put it like that, according to the problem as an analog thing, whether it's a digital signal as an FPGA, where you try to solve a specific task, as you say, or an analog computer where you try to model a particular problem like a differential equation, for instance. So programming for both means actually building the kind of circuitry.
Yeah, exactly. It's very highly specialized. You're not trying to build, generally speaking, a generic machine. Usually what you're doing is you're thinking, say, I've got some input signal and I want my output signal to be some function of that input signal. So how do I build a circuit that will modify that signal, that will transform that signal into an output with the correct relationship to the input? So in both cases, you're kind of using pieces that you're familiar with to sort of create the changes, the transformations to the data that you want, whether that data is continuous or digitized. To some extent, that means that these designs are like, they're quite rigid. So it's computing, but I don't think of them as computers. Because I think when we think of computers, we think of this very generic Turing machine, universal Turing machine type thing. The idea of a machine that can sort of do anything. Not like the correct definition of computation. Like computation, it doesn't have to be generic in that way. But that's, I think, what normally comes to people's head when you say like a computer, because that's what we're used to using. Instead, both analog computing and with most FPGA designs, you are dealing instead with the circuit is the solution to the problem.
Indeed.
Circuit in an analog or FPGA context is like a single program, if you were thinking in like a normal computing context.
If you're interested in FPGAs, and I hope you are, you can find out more about them through the links I included in the show notes, including a link for the Go board Michael mentioned, the affordable FPGA board from the company called Nandland, which also has other documents on FPGAs and how to program them with a hardware description language. Next week, we're going to look at something very different. We're going to look at a package manager, yes, one of those, and it's called Pixie, where I had the pleasure to talk to one of the SSI fellows, Ranier, but also the CEO of the open source company behind it. I hope you tune in then. Thanks for listening. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.